Okay, so picture this, right? You're in Greenland,
Hmm.
way up north, right? And it's like ice and glaciers as far as the eye can see.
Yeah, stark landscape.
Like, totally. But then you look down, and right there at your feet are these, like, perfectly preserved dinosaur footprints.
Wow.
I know, right? Three-toed footprints from dinosaurs that were roaming around, get this, 200 million years ago.
That's incredible to think about those ancient creatures walking where we stand today.
It's wild, right? And that's what this whole deep dive is about, how something as, I don't know, seemingly random as dinosaur footprints can unlock this, like, crazy story.
It's all about connections, isn't it?
Totally, yeah. Connections across, like, vast stretches of time.
Deep time.
Deep time, for sure. And we're talking the movement of continents, massive climate swings, and even, believe it or not, our own human origins.
It's all intertwined, these seemingly disparate events across millions of years.
Exactly. And for this one, we're tapping into this really vivid account of a paleontology expedition to Greenland. You'll feel like you're right there with the researchers when they find these incredible footprints.
I love those firsthand accounts.
Me too. They're the best. And of course, we'll be weaving in the science, all the essential explanations of how Earth's climate has changed over, well, forever.
So basically, we're going to try and connect the dots between those dinosaur footprints frozen in time in Greenland, the slow but powerful forces that created the Himalayas.
Oh, and don't forget the currents swirling around Antarctica.
Oh, right. And even those subtle wobbles in Earth's orbit.
Because, you know what, those seemingly small things have had huge consequences for life as we know it, including, well, us.
Absolutely, shaping the very course of evolution.
Okay, so let's set the scene. It's 1989, summertime in Greenland, second summer of this paleontology project.
Okay.
And their author, they described these, like, super eerie lenticular clouds hanging over the fjord, even had a nickname for them. Flying saucer clouds.
I've seen pictures of those. They look otherworldly.
Totally otherworldly. And these, like, stacked discs just hovering above the peaks.
Yeah.
They were beautiful, but also a sign that a polar windstorm was on its way.
Ah, so they were a warning sign.
Yeah, basically. See, those lenticular clouds form when moist air gets forced up over mountains.
Right, like squeezing it out.
Exactly. And as it rises, it cools down and condenses, forming those lens-shaped clouds.
Nature's artwork with a hidden message.
Right. So anyway, this particular morning, the author and another grad student, Steve Gatesy, they set off on this trek to the coast.
Looking for fossils.
Yep, that was the mission, hunting for dinosaur bones.
Well, they had already found some other fossils, hadn't they?
Yeah, at other sites, bits and pieces, teeth, fragments, the usual stuff.
Still exciting, though, right? Finding those clues.
Oh, for sure. And these were all from the Triassic period, the time when dinosaurs were just starting to, like, diversify and take over.
The dawn of the dinosaur era.
Exactly, and they had these aerial photos and geological maps suggesting there might be some promising rock exposures along the coast.
So hoping to find some new fossil hotspots.
You got it. It's like a treasure hunt, but with ancient bones.
And it's not always easy, is it, finding those fossils?
Nope, not at all. Paleontological fieldwork, it's a lot of planning, but also, a good dose of luck and being in the right place at the right time.
Serendipity.
Totally. So they spend the morning, Steve and the author, climbing the sandstone peak. Tough climb.
Wow.
Yeah, and it ends at this, like, dramatic bluff overlooking the Arctic Ocean.
Breathtaking view, I imagine.
Oh, definitely. But in terms of fossils, total bust.
Nothing. Oh, no.
Yeah, not a single bone. But they have this peaceful lunch right on the edge of this massive cliff.
Red cliff, wasn't it?
Yeah, bright red, plunging straight down 1,500 feet into the ocean.
That's a sheer drop.
No kidding. So they're surrounded by these layers of red and green rock, sculpted by, ice and wind and water over millions of years.
A reminder of the immense forces shaping our planet.
For sure. And they could have stayed up there all day, but the weather was changing, and they had a long hike back to camp.
Right. Back across the valley.
So they start making their way down, and it's like this natural staircase of sandstone, siltstone, shale, with these flat ledges appearing every, 50 feet or so.
Making their descent a little easier, I suppose.
Yeah, but get this. Every now and then, they'd catch a glimpse of these hoodoos.
Hoodoo.
Yeah, they're these, like, naturally eroded sandstone pillars.
Oh, I've seen pictures of those. They're so strange.
They are. Totally bizarre.
Yeah.
Like these ghostly figures watching them.
Spooky.
A little bit, yeah. Anyway, they were moving pretty fast, heads down, focused on not tripping.
Probably missing all sorts of potential fossils in their haste.
Probably, yeah. So they reached this one particular ledge, huge, like 2 football fields long.
Wow, that's massive.
Yeah, and the author stops for a second, catches their breath, glances down, and there it is. A dinosaur footprint. I know, right? Clear as day. 3 toes, sharp claw marks, a carnivorous dinosaur.
Talk about a heart-stopping moment.
I know, right? And then they look closer and realize it's not just one footprint, it's a whole trackway, like 10 steps in a row.
So they could actually follow the path this dinosaur took.
Exactly. But then, it gets even crazier, they see another set of 3-toed prints intersecting the first trackway.
Wow, so there were multiple dinosaurs in the same area.
It was like a dinosaur highway. The whole ledge was covered in tracks, big ones, small ones, all overlapping.
Like a snapshot of a bustling dinosaur community.
Totally. And what it tells us is that 200 million years ago, this was probably the muddy edge of a lake, a place where dinosaurs were constantly coming and going.
Leaving their mark.
Literally.
Okay.
And they even named this spot the dinosaur dance floor because of, the sheer number of footprints.
That's a fitting name.
Right. And it gets even more interesting because these weren't just any old dinosaur footprints. They had this distinctive shape, a long middle toe, shorter toes on either side.
Like a bird's foot, almost.
Yeah, and way back in the 1850s, a geologist named Edward Hitchcock, he found similar tracks in Massachusetts.
Massachusetts. That's quite a distance from Greenland.
I know, right? But these footprints, they're like a clue connecting these distant places.
Fascinating.
Yeah, so Hitchcock, he called these tracks Grallator cursorius, which means wading bird.
Makes sense, given the shape.
Yeah. And since then, they've found grallator tracks all up and down the eastern coast of North America.
So these dinosaurs were widespread across what we now know as separate continents.
Exactly. And it's not just the footprints. The rocks themselves tell a similar story. The same red and green sandstone found in Greenland, you find it in eastern North America, Morocco, even parts of Western Europe.
That's quite a spread.
It is, but it makes sense when you remember Pangaea.
Ah, the supercontinent.
Yep, 200 million years ago, all those land masses were mashed together, one giant continent.
So dinosaurs could literally walk from Greenland to Morocco.
Without getting their feet wet. And those rocks, they formed right around the time Pangaea was starting to break apart.
Leading to the continents we know today.
Yep, North America splitting off from Africa and Europe, the Atlantic Ocean forming, and, get this, all that continental movement had some major effects on Earth's climate.
Some pretty chilling effects, as the author puts it.
Yeah, no kidding. But before we get into that, we need to talk about carbon.
Carbon?
Yep, the carbon cycle, the long-term one, because it's key to understanding how Earth's climate changes over millions of years.
Okay, I'm intrigued.
So while those paleontologists were out there in Greenland finding footprints back in the 19th century, there was this French scientist, Jacques-Joseph Ebelman.
Okay.
And he wasn't out on expeditions. He was at home working out equations.
A different kind of exploration.
Totally. But his work was just as important because he came up with this theory about how rock weathering affects the global carbon cycle.
Rock weathering.
Yeah, basically how rocks break down and erode.
Oh, okay.
And at the time, his ideas were way ahead of their time, so they were kind of ignored for over 100 years.
Happens sometimes in science. A truly groundbreaking idea can take a while to catch on.
For sure. Now, when we think about ice ages, right, the first thing that comes to mind is usually changes in sunlight.
Right. Less sunlight, more ice.
Makes sense. But here's the thing. The sun's actually getting brighter over time.
What? How's that possible?
It's because of nuclear fusion. The sun's constantly producing more energy.
So the Earth should be getting warmer, not colder.
Exactly. Which means something else must be driving those long periods of cooling, those ice ages.
So it's not just about how much sunlight we get?
Nope, it's more complicated than that. And that's where carbon comes in, specifically greenhouse gases like carbon dioxide.
Ah, the greenhouse effect.
You got it. It's like a blanket around the Earth, trapping heat.
And this idea was first proposed by...
Joseph Fourier, another brilliant scientist from the 19th century.
Right, he recognized that certain gases in the atmosphere can trap heat, preventing it from escaping back into space.
Yep, and later on, Svante Arrhenius figured out that if we increase carbon emissions, like from burning fossil fuels, the Earth will warm up.
Which is what's happening now with climate change.
Exactly. But let's go back to the time before humans, before we were pumping all that extra carbon into the atmosphere.
So what was the main source of carbon back then?
Volcanoes.
Volcanoes.
Yeah, they're constantly releasing gases,
Wow.
including carbon dioxide, from deep inside the Earth.
So over millions of years, volcanoes have released a massive amount of carbon.
Absolutely.
Yeah.
But here's the key. There also needs to be a way to remove carbon from the atmosphere Otherwise, the Earth would just keep getting hotter and hotter.
Makes sense. So what's the counterbalance to volcanoes?
Rock weathering. That's where Ebbelman's work comes in.
Oh, right. You mentioned that earlier.
Yeah, so here's how it works. Carbon dioxide in the atmosphere mixes with water and forms carbonic acid, basically weak acid rain.
Okay.
And this acid rain falls on rocks and slowly dissolves them, breaking them down. And those dissolved bits, they contain carbon, they get carried by rivers and streams into the oceans,
Okay.
and eventually they settle on the ocean floor, get buried, and over millions of years, some of that carbon gets recycled back into the Earth.
And eventually released back into the atmosphere through volcanoes.
Exactly. It's a cycle, a long, slow cycle, taking about 100 million years.
Wow. So Earth's climate is this balancing act between carbon being released and carbon being absorbed.
You got it. And anything that changes the rate of rock weathering, like, say, mountain building,
Yeah.
can have a big impact on global temperatures.
Makes sense. So mountains can actually cause the planet to cool down?
Exactly. And
Yeah.
there's actually some scientific evidence to support this whole carbon cycle idea.
Oh.
Yeah, back in the 1980s, some scientists looked at geological records of volcanic activity and rock weathering, and they found a link between those things and global temperatures over the past 500 million years.
So Ebbelman was onto something.
Big time. But it was another scientist, Harold Urey, who really brought these ideas into the mainstream.
Harold Urey, wasn't he a physicist?
Yeah, a brilliant one. He worked on the Manhattan Project during World War II.
Wow. So he was involved in developing the atomic bomb?
He was, but after the war, he turned his attention to planetary science.
And he independently came up with the same carbon cycle theory as Ebbelman?
Yep. He saw Earth as this complex system of atoms and chemicals all interacting.
That's a fascinating way to look at it.
It is, and his work helps solidify the idea of a long-term carbon cycle regulating Earth's climate.
And he even won a Nobel Prize for his work, didn't he?
He did, but he actually skipped the ceremony to be there for the birth of his daughter.
What a guy.
A true maverick, right? So now we've got this understanding of the carbon cycle, but how does that explain why the poles froze over?
Yeah, that's a good question. How do we go from this long-term carbon cycle to ice caps?
Well, that's where Maureen Ramo comes in. She's a big name in earth science.
I've heard of her. She's done a lot of work on past climates.
She has. And she was really interested in figuring out why the Earth cooled down so much in the millions of years before the poles froze.
So she was looking for the trigger, the thing that tipped the balance towards ice.
Exactly. And she realized that the answer might lie in the movement of continents, specifically the formation of the Himalayas.
The Himalayas.
Yeah, you see, about 60 million years ago, India was an island continent drifting north.
Okay.
And eventually it slammed into Asia, a slow-motion collision, but incredibly powerful.
And that created the Himalayas.
Yep, the mountains were pushed up as the two continents collided.
Wow, so mountain building is literally continents colliding.
It is. Pretty mind-blowing,
Yeah.
right? So Ramo's idea was that this uplift of the Himalayas, it exposed a huge amount of fresh rock to the elements.
Ah, more rock weathering.
Exactly. And more rock weathering means more carbon dioxide being pulled out of the atmosphere.
Leading to global cooling.
Precisely. So the rising Himalayas were like a giant carbon sink, slowly cooling the planet.
And is there evidence to support this theory?
There is. They found it in ocean sediments, chemical signatures showing increased rock weathering, coinciding with the rise of the Himalayas and global cooling.
So the pieces fit together.
They do. But here's another puzzle. The planet started cooling down about 47 million years ago, but the big ice sheets in Antarctica, they didn't form until about 15 million years ago.
So there was a lag between cooling and ice formation.
Yeah, a big one. And Antarctica was already at the South Pole, so you'd think it would have frozen over sooner.
So what caused the delay?
Well, it has to do with the breakup of Gondwana, another ancient supercontinent.
Okay.
So as Antarctica separated from the other land masses, it became surrounded by ocean.
Isolated.
Totally. And this allowed for the formation of a very important current, the Antarctic Circumpolar Current.
I've heard of that. It's a powerful current, isn't it?
Extremely powerful. It circles all the way around Antarctica, uninterrupted.
Oh.
And this current, it acts like a barrier, keeping warm water from the north away from Antarctica.
Ah, so it isolated Antarctica climatically as well as geographically.
Exactly. And that's what allowed it to finally freeze over.
Interesting. So it wasn't just about the planet cooling down. It was also about the isolation of Antarctica.
Yep. Both factors were crucial.
But then there's the Arctic, right? Why didn't it freeze over at the same time?
Good question. And the answer lies in ocean currents, specifically the Gulf Stream.
The Gulf Stream, that's the one that brings warm water up towards Europe.
You got it. And for millions of years, it's also been bringing warm water up towards Greenland.
Keeping it relatively warm.
Exactly. But here's where things get really interesting. The strength of the Gulf Stream depends on the difference in salinity between the Atlantic and Pacific Oceans.
Salinity, you mean how salty the water is?
Yep. The saltier the Atlantic, the stronger the Gulf Stream.
Okay, so how did the salinity change?
Well, for a long time, the Atlantic and Pacific were connected by a seaway between North and South America.
So water could flow freely between them.
Exactly. But then, starting about 15 million years ago, things started to change. The tectonic plates in Central America began colliding.
Uh-oh, sounds like trouble.
It was, geologically speaking. Volcanoes erupted, islands formed, and eventually those islands joined together to form what we now know as the Isthmus of Panama.
The Isthmus of Panama.
Yep, the narrow strip of land that connects North and South America.
So that closed off the seaway between the oceans.
Completely, about 3 million years ago.
Wow, so that one geological event had huge consequences for the oceans.
Massive consequences, because now the Atlantic and Pacific were separated and their salinity started to change.
The Atlantic got saltier.
Exactly, which made the Gulf Stream even stronger, bringing more warm, moist air to the Arctic.
Which paradoxically led to the Arctic freezing over.
I know, it seems counterintuitive, right? But that extra moisture meant more snowfall, and eventually that snow compacted into ice, forming the Arctic ice cap.
So it was a complex chain of events, continents moving, currents shifting, salinity changing.
All culminating in a frozen Arctic.
It's amazing how interconnected everything is.
Totally. And with the Earth in this new colder state, even small changes in sunlight could now trigger those massive swings between glacial periods and warmer interglacial periods.
The ice ages.
Exactly. And that's where Milutin Milankovic comes in. He was a Serbian mathematician who figured out the astronomical reasons for these ice ages.
Astronomical.
Yeah, it's all about Earth's orbit around the sun.
Okay.
So Earth's orbit, it's not a perfect circle, it's slightly elliptical, and that ellipse changes shape over time about every 100,000 years.
Okay.
And the tilt of Earth's axis, it also changes about every 41,000 years.
So Earth's wobbling around like a top.
In a way, yeah. And it also wobbles on its axis, completing a full wobble about every 26,000 years.
So we've got 3 different cycles going on.
Exactly. And Milankovitch realized that these cycles, they affect how much sunlight different parts of the Earth receive at different times of year.
So they can influence the growth and melting of ice sheets?
Precisely. And for a long time, this was just a theory. But then in the 1960s, scientists started analyzing deep-sea sediments.
Looking for clues about past climates.
Yep. And they found evidence that ice ages had indeed come and gone in cycles that matched Milankovich's calculations.
So he was right.
He was. It's incredible, isn't it? We've got continents crashing together, oceans changing, and the Earth wobbling around the sun.
And all of that leading to these massive ice ages.
And those ice ages, they weren't just abstract events. They shaped the world we live in today.
In so many ways.
Seriously, during the last ice age, which peaked about 26,000 years ago, huge ice sheets covered much of North America, Europe, Asia.
Thousands of feet thick.
Yeah, imagine that. Ice covering Chicago, New York, everything.
And sea levels were much lower, right?
Way lower, like 400 feet lower.
So coastlines were completely different.
Totally different. And as those glaciers melted, they carved out valleys, created lakes, sculpted the landscape.
Like massive bulldozers.
Exactly. And it wasn't just the landscape that changed. Plants and animals had to adapt or die.
So entire ecosystems shifted.
They did. And some animals even evolved in isolation as the ice separated populations.
Like polar bears, right?
Yep. They evolved from brown bears that got stranded by the ice.
So in a way, the ice ages created new species.
They did. And they also played a major role in human evolution.
Really?
Oh, yeah. Our early ancestors were in Africa. But as the climate changed, they started migrating, adapting to new environments.
Driven by the ice ages.
In part, yeah. And some of those migrations led to the evolution of different human species, like Neanderthals.
Neanderthals, they were adapted to the cold, right?
They were. They lived in Europe during the ice ages, and eventually they were replaced by our own species, Homo sapiens.
And Homo sapiens also migrated during the ice ages.
Yeah, they crossed the Bering Land Bridge into North America when sea levels were lower.
So we're all connected to these ancient events.
We are, and the legacy of ice continues to this day.
In what ways?
Well, it affects sea levels, coastlines, fishing areas, weather patterns, even global trade routes.
It's still shaping our world.
It is, even though we might not always realize it. It's like that parable the author mentions about the fish who don't know they're in water.
It's all around them, but they're unaware of it.
Exactly. And for us, ice is kind of like that, this powerful but often unseen force that's been shaping our planet for millions of years.
And now we're changing that ice rapidly with climate change.
We are, which brings up a big question. What happens when we disrupt this ancient balance? What does the future hold for a world without ice?
That's something for all of us to think about.
It is, and it all started with those dinosaur footprints in Greenland, a reminder that everything is connected across time and space.
And that our actions have consequences that ripple far beyond what we can immediately see.
So as we wrap up this deep dive, I think it's safe to say that ice, it's more than just frozen water.
It's a force of nature, shaping our planet and our destiny.